Yeah, very good morning. Am I audible?
You are audible.
Let me share my screen. Yeah, screen is visible.
Yes, sir.
Yeah, fine. Thank you. Yeah. So okay, so do you have any doubts to ask? Yeah.
Audible?
Yes.
Yeah. So, sir, in the last lecture, example 3, like the end you told us to.
Uh-huh. Okay. Means okay. Example three. So example two we have solved. Example three. Yes.
So, yeah, how should we like approach when we then?
So I this is a similar problem what we have discussed. It's like in a theoretical way. Okay. So
When
if
Lagrange?
uh, Lagrange word has not come so far. You have this. See, you want to get the corresponding PD for this problem f of x plus y plus z, comma, and x square plus y square plus z square plus z square equals to 0. Yeah. So you want to find this associated PD. So what I have suggested, this you may call this as a function u. This is a function v. Okay, this is an arbitrary function. Okay, so we have discussed one problem when you have f of u comma v equals to 0, where u is a function of xyz and v is a function of xyz, and how to find the corresponding PD. So this is here, let u equals to x plus y plus z, v equals to x square plus y square plus z square. So from here, you have now every information from here. Ux also 1, Vx, Ux, Uy, and Uz. These three values are 1. That's very clear, partial derivatives. Vx is 2x from here. Vy is 2y. Vz is 2z. Okay. Now you differentiate partially with respect to x and partially with respect to y. So you have, if you start with f of u comma v equals to 0. So you call this as 1. Okay, where u and v are the functions which has been defined so far. Okay, previously now. Okay, so differentiating 1 partially with respect to x, we get, so what we get is fu, okay, and ux plus you have this is uz and zx plus fv time vx plus vz time zx equals to 0. Since, see, we are differentiating partially with respect to x. X and y are treated to be independent variables. Z is a dependent variable on x and y. That is our assumption, basic assumption. Okay, so I may means like ux time dou x by dou x. So x partial derivative with respect to x is 1. U with respect to y, then y partial derivative with respect to x, since y is the independent variable, the partial derivative of y with respect to x is 0. So that's why the second term is not here. Now this will now give you this information. So fu, so ux and uz are 1. It is 1 plus p. Zx we have denoted by p. Fv time Vx was 2x and Vz was 2z. So you have 2 time x plus pz equals to 0. So that you can call as 2. Now similarly, differentiating 1 partially with respect to y, we get the following. Okay, so fu uy plus uz zy plus fv time vy plus vz zy equals to 0. Now you have all the information. You can substitute. Now fu uy is 1, uz is also 1 plus q plus fv time 2 time y plus qz is equals to 0. So you have, this is a third equation. Now from so 2 and 3 can be written in the following matrix form. If you recall, u fv is equals to 0 0, and you have, this is I think 1 plus p, and you have, this is 2 times x plus pz, and fe is 1 plus q, 2 times y plus qz. Now we are interested in a non-trivial solution. So for existing non-trivial solution, okay, so the determinant of this coefficient matrix should be 0. Okay, should be a singular matrix. If it's a non-singular matrix, invertible, and its inverse exists, you will get a only trivial solution. Okay, so this is so therefore for non-trivial solution, so you are eliminating actually fu and fu, or you can, okay, both. So we have this determinant of 1 plus p, 2 times x plus pz, 1 plus q, 2 times y plus qz is equals to 0. Now you know how to solve this. So 2 times 1 plus p times y plus qz plus 2 times 1 plus q times x plus pz is equals to 0. This 2 will get cancelled, and you can now simplify it. So this will be, so you can further simplify it. Okay, and so your associated partial differential equation is given by this. Okay, yeah. So this is, if you solve it, you will get in the following manner. Okay, so you can do that. Okay. Right. So this is I think this will not match because I think this is not here.
Will be a
Right. Huh?
minus sign will come. Determinant.
Here minus. Thank you. Yeah. So if minus is come, so this PQZ will get cancelled with PQZ. So that's why I was worried about it. Now, now whether you are getting simply or simplification. simplification the same thing. Okay, so that we can match now. Okay, so y plus qz plus py plus pqz minus okay, minus x minus bz minus qx minus pqz is equals to 0. So pqz will get cancelled. So y minus x will be sent to on the right side, and you have p coefficient is y minus z plus q coefficient is z minus x. Right? 4 terms are adjusted. That's equals to x minus y. Yeah, you can see. Okay, so this is how you will solve such type of problem. Now, let's go further. Next problem. Let us consider the following integral surface. Z equals to x into y plus f of x square plus y square. So it will denote any family. Okay, any function of x square plus y square. So f is an arbitrary function. So one arbitrary function will correspond to the first order. One, okay, corresponding to the order means like here number of arbitrary function is 1. So first order partial differential equation will be there. If you have 2 arbitrary functions, it will correspond to the second order. Okay, so if you solve this problem, okay, so again you will solve in the same way. Your goal is to eliminate this arbitrary function in the process, f of x square plus y square. So you can call this as 1. So now differentiating 1 partially with respect to x, what we get is zx is p is equals to y plus 2x times f dash of x square plus y square. So this implies f dash of x square plus y square is equals to p minus y by 2x. Okay, now differentiating 1 partially with respect to y. So again, you can use the symmetry or you can differentiate once more, and what you will get is zy is q is equals to x plus 2y times f dash of x square plus y square, and that will imply f dash of x square plus y square must be equals to q minus x by 2y. So you can call this as 3. You can call this previous as 2. So from 2 and 3. So from 2 and 3, we get the following, right? P minus y by 2x is equals to q minus x by 2y. We will get cancelled. Now you can simplify it. So p y minus y square is equals to q x minus x square. So this implies p y minus qx is equals to y square minus x square. Anyway, you can represent. Okay. So this is the final associated PD for this. Okay. Right. Now, in the example 5, so let us consider the following family of integral surface z equals to f of x into y by z. So again, you will proceed in the similar fashion. Z equals to f of x into y by z. So you can call this as 1, differentiating 1 partially with respect to x, we get, so p equals to f dash of x into y by z. Now you have to apply the u by v rule, right? So z square z time partially with respect to x x into y derivative with respect to x is y minus x into y time z derivative. So that's the p. Okay. So this implies f dash of x into y by z is equals to p times z square divided by yz minus xyp. This is called 2. Now, similarly, again, differentiating one partially with respect to y, partially with respect to y, we get. So, so z, what is that? Z equals to f of x into y by z. So, if you differentiate one partially with respect to y, what you will get is q is equals to f dash of x into y by z time q by v rule again, z square z time x into y partial derivative with respect to y is x minus x into y cube. So this will imply f dash of x into y by z is equals to q times z square divided by zx minus x into y into q. You can call this as 3. Now from 2 and 3, so from 2 and 3, we get you have this is pz square divided by yz minus x into yp is equals to qz square divided by xz minus x into y into q. Right? Yes. Now you have this z square is eliminated. Now you can cross multiplication apply and you can find out the simplified form. So what you have is pxz minus xypq is equals to qyz minus xypq. This will get cancelled. So this will implies you have pxz minus qyz equals to 0. Okay. So this will be the, so you can further simplify because z is a non-zero because you're not interested in the trivial solution. So again, this is px minus qy equals to 0. Okay, since z is non-zero, we are assuming that z is non-zero because you are not interested in a trivial one. You are interested in a non-trivial. Okay, right. Okay, so you have finally px equals to q. Right now, I think this is the last example about the formation of PD. So we are interested in finding the PD of family of planes, the sum of whose x comma y comma z intercepts is equal to unity. So if you recall, what is the intercept form of the equation of plane? Is when you have the intercepts on x-axis, y-axis are a0, 0, 0, b0 and 0, 0, c. The equation of that plane is x by a plus y by b plus z by c is equals to 1. So this is the equation of plane. And it is given that the sum of whose xyz intercept is equal to unity. So condition is a plus b plus c is equals to 1. So here again we will treat that x and y as a dependent variable, independent variables and z as a dependent variable. Okay, and you proceed in the similar fashion. So you have x by a plus y by b plus z by c is equals to 1 with the condition of condition that sum of the intercept is 1, a plus b plus c is equals to 1. Now partial derivative with respect to x, okay, so you can call this as 1. So differentiating 1 partially with respect to x, we get 1 by a plus you have here zx. So that is zx is p by c is equals to 1. Okay. Now similarly, so from differentiating 1 partially with respect to y, what we get is 1 by b plus q by c is equals to 1. Sorry, 0, right? Derivative 1. Now, note that this equation is involving a and c, and this equation is involving b and c. Okay, so here we are going to use, this is, you can call this second, this is third, this is fourth. So from 2 and 3, you can replace c by 1 minus a minus b. Okay, and here also. Okay? So from 3 now, so what is from 3 is 3, what it tells you, what it gives you is 3 will give you, so let's simplify it. Okay, so what 3 will gives is p is equals to minus c by a, right? Yeah, and what is c is you have, this is 1 minus a minus b divided by a. Now 4 will give you q is equals to minus c by b, right? And that's going to be minus 1 minus a minus b divided by b. So our aim is to eliminate these a and b, okay, these arbitrary constants. Okay, so what you can do is now you can have two equations in two unknowns, right? This is using 2. Okay, so now further, this implies, I may write it that this is AP, okay, plus 1 minus a minus b is equals to 0. Okay, that first equation. Okay, which gives you, this implies a into, so p minus 1 times a minus b is equals to minus 1. Right? Now, similarly, you have from here bq plus 1 minus a minus b equals to 0. This implies you have a minus a plus b minus, not b minus, so plus q minus 1 b is equals to minus 1. Okay, so you can also get rid of this minus sign, okay, by multiplying by minus. So I may write a more simplified form now. So let's multiply by minus both sides. So what you will have is 1 minus p times a plus b is equals to 1, and you have a plus 1 minus q times b is equals to 1. Now you have two equations in two unknown, right? Yes, you have two equations in two unknowns. You can solve this now you can multiply it by 1 minus p, or you can multiply above by 1 minus q and then subtract okay, and then subtract. So what you will get is, if you subtract, so a will not be more, so you have 1 minus p into 1 minus q times b is equals to 1 minus p. So this will be implies, so 1 minus, so now open, so 1 minus p minus q plus pq, okay, time b is equals to 1 minus 1 plus p, so that's p. So this gives you 1 will get cancelled, so you have this is p plus q minus p times q, p is equals to p. So this will implies b is equals to p divided by p plus q minus pq, right? P plus q minus pq. Okay, now when you have b, you can have a. So what is a is, now a is equals to 1 minus, the second equation, 1 minus q times b. So this is equals to 1 minus q times p divided by p plus q minus pq. So now you can take this LCM, p plus q minus pq. So you have, this is p plus q minus pq minus p plus pq. So pq will get cancelled, p will get cancelled. So what you will have is q divided by p plus q minus pq. Now from here also you can get c. Okay, what is c is 1 minus a minus b. Okay, so you can also get this c. Now 1 minus p divided by p plus q minus pq minus q divided by p plus q minus pq. Now you take this LCM, and what is the final is p times q, right? So p plus q will get cancelled with minus p minus q. So you have all this now. Okay, so now you can substitute in that intercept form. That's x by a plus y by b plus z by c is equals to 1. Substitute here. So 1 by a. So from here 1 by a is p plus q minus pq divided by q. So you can further simplify by p. Right? A is with q, right? Okay. By q, x plus p plus q minus pq divided by p, y plus p plus q minus pq divided by pq, z is equals to. Now you can further simplify it, multiply both sides by pq. Okay, take LCM pq and you just more simplify it. Okay, so what will be the final expression will be the following. Okay, this will be the following expression at the end. Okay, right. Now we are going to focus on now quasi-linear PD. Okay, so quasi-linear PD means we are talking about the first order one only. Okay, so so as we can recall here, we will say first order PD is a quasi-linear when you have P coefficient and Q coefficient as a function of X, Y, Z only. And the rest of the things are function of X, Y, Z on the right side. Okay. So now what you can here first, if you try to look at, suppose you have the solution. Okay. Solution is a integral surface which is given by f of x comma y comma z equals to 0 is equals to, we can write it as z of x comma y minus z is equals to 0. This is the equation of integral surface. If it is, means if it is solvable, if you are able to solve this equation, the solution will be, this is an implicit form, this is an explicit form. Okay, so so this is okay. Now the integral surface, if you look at carefully, we know already aware about from the vector calculus that grade f will give you the normal to the surface. So what is the grade f here is you have zx comma zy comma minus 1. And what are these in notation? That is going to be p, q, and minus. So that gradient vector will give you the normal to that integral surface. If everything is nice, you have you can differentiate partially with respect to x and so on. Now, what it will give us, okay, what it will, how it will help you to analyze further properties of the integral surfaces as follows. Now, if you look at this PQ minus 1 vector, okay, so, and if you look at this equation, this is equation 1 and this is equation 2. So, from 1 and 2, you can easily observe that this vector P, Q, and capital R is going to be orthogonal to this gradient. At any point, if you fix any point x, y, z, this P, Q, R is orthogonal to grade f. Of course, we are talking about the grade f which is non-zero vector. Okay, normal which is non-zero. Okay, so what one suggests you that this capital P, capital Q, and capital R, this will give you, this is a vector, it will identify a direction. Okay, so it is a vector which will identify a direction. So of course, vector having two things, magnitude and direction. Okay, so it will identify also direction of moving, okay, of a flow or of a gas or something, okay, of a velocity and so on, okay, of a liquid. Now, at any point, PQR is going to be orthogonal to the normal to the. So, what it suggests you further now is that this vector directions are going to lie in the tangent plane, okay, because normal is going to be the perpendicular to the tangent. Okay, so this PQR will lie in the tangent plane to the surface. Okay, so this will also identify the direction which will be give as which we will give name as characteristic directions. Okay, and we will also identify some name for characteristic curve. Okay, which we further call it like a solution curve. Okay, so you will if you are having suppose in XYZ space, okay, so you have XYZ space, so you have a curve C. Okay, so it is so at any point, if you choose any point, suppose you choose any point, okay, so this P, Q, and R, this vector at any point will identify a direction, and together it's going to be lie in a tangent plane to the integral surface. Okay, and if you include this direction at every point, so it may generate a field, direction field. Okay, characteristic direction field. Okay, now note that if along the curve, if suppose you draw the tangents, okay, along the curve, if you draw the tangents, okay, at any point, if you draw the tangent, if they are compatible or not compatible, I should say, they are going to move along this characteristic direction. Okay, means at any point it's going to be matched with the direction of PQR at some point in the integral surface or the tangent plane of the integral surface. Then this curve is called as a characteristic curve. Now you can now further talk about this means like parameterization of the curve. Suppose parameterization of the curve is x equals to x of t, y equals to y of t, and let's take z equals to z of t. Then you know how to find the direction of the tangent vector is dx by dt, dy by dt, dz by dt. But they are going to be matched along this characteristic direction field. So that will lead to the following ordinary differential equations: dx by dt equals to p, dy by dt equals to q, dz by dt equals to r. They should match with this. So you will get a system of ODEs here, ordinary differential equations. And if you take a point, suppose you take an initial point, let's take x naught, y naught, z naught, means at t naught, t equals to t naught, initially time is 0 or whatever, at t naught, t is equals to 0 or whatever at initial what second you will start with. Okay, suppose you are trying to identify a characteristic curve through this point, then ODE theory will give you guarantee that there is a unique characteristic curve. Unique means there is a such unique characteristic curve provided this P, Q, and R are sufficiently smooth. Okay, so we are going to now look at this. Okay, so keep following. So let's I'm just going to repeat now something which we have just now spoken. Okay, so let initial surface or possible solution surface can be found. Okay, then you have the surface equation is f of x, y, z equals to z of x, y minus z equals to 0. So one is implicit form, another is explicit form. Now the gradient vector is going to be the normal to integral surface f of x, y, z equals to 0. That we just talked. Okay, so now from given PD, we can observe that this PQR is orthogonal to gradient. Okay, so therefore it lies in the tangent plane of the surface. Okay, so lies in the tangent plane of the surface at each point wherever this gradient f is normal, is a non-zero vector. Okay, so this direction, the direction determined by the vector at each point is known as characteristic direction. Okay, and together if you make this if you keep all things together, means like these all directions together, this will generate a direction field. Okay, now a curve in xyz space whose tangent at every point coincides with the characteristic direction field is called a characteristic curve. So just now I have told you, okay, that characteristic curve definition. At every point the tangent is going to be in the same direction of the characteristic direction. Okay, now so the parametric equation of the characteristic curve be this. Now you know what will be the tangent vector to this curve is given by this at any point. So, but they both, if you are talking about a characteristic curve, so they lie along the direction of the characteristic direction field. So you will have the following ordinary differential equation. Okay, so right hand side is also a function of t, because once you know x is a function of t, y is a function of t, z is a function of t. So right hand side also you can replace x by function of t, y by function of t, z by z function of t. Okay, so it will be okay. So it will be a system of ODE to solve So these equations are called characteristic equations of PP plus QQ is equals to R. So do you have this quasi-linear PD? Okay, and these equations, this ordinary differential equations are called characteristic equations of this. Okay, so we have some attached name with this. Okay, because its characteristics is suggested name because it characterizes the solution. Okay, so this is why this name has come. Okay, and the solutions of these equations, so every solution, so if you find out this, if you try to identify the solution for these characteristic equation, it will lead to a curve. Okay, so these curves are called the characteristic curves of the quasi-linear PD. So when you are asked to when you have been asked to identify characteristic curve of certain quasi-linear PD, okay, then you are supposed to solve the system of ODE. Okay, right. So this will give you the uniqueness as per the ODE theory. So assume that PQR are sufficiently smooth and they do not vanish at all at the same point. Now, then from the theory of ODE, we observe that there will be a unique characteristic curve passes through each point, say x0, y0, z0. So ODE theory will support you whenever you are initializing at the point. So you know initial value problem, if you recall, from the ODE, dy by dx equals to f of x comma y with y at x0 equals to y0. Okay, if you recall, you need this initial condition is required, okay, to establish the uniqueness. So this is why here you have to initialize the point. Okay, now to solve, if you want to solve this IVP, PP plus QQ is equals to R, we pass a characteristic curve through each point of initial curve C given by initial value problem. So we'll see. Okay, so these curves generate an integral surface, which is the solution of the IVP. So these all curves, if you take together, it will generate a surface, which we'll call as integral surface, and it will be the solution of the IVP. Okay, right. Now, so if you want to write characteristic equation in non-parametric form, so you can, so you have the equation in parametric form was dx by dt equals to p, dy by dt equals to q, dz by dt equals to r. So if you want to write in non-parametric form, so you have certainly with this. So I think this is easy to observe. Dx by p equals to dy by q equals to dz by r. Now, so this finally method of characteristic or the method of Lagrange to solve or to find the final find the general solution of the quasi-linear PD. So we will go to the proof maybe in the next session. Okay, but we will try to solve the problem. Okay, first. So the general solution of the quasi-linear PD is going to be of this form: P of u comma. So phi is some, so don't go with this notation phi. So instead of phi, you can write f, capital F or small f, whatever, g, h, an arbitrary function of u and v, two parameters, or means not two parameters, two functions. Okay, so is equals to 0. So what are these u and v? Are nothing but the u and v are going to form a solution of this equation. So characteristic equations. Okay, how would we find out these families of solutions? That we are going to look at through the problems. Okay, right. So let's go with the example 1. So I will come back to the proof a little later. Okay, so let us consider this problem, and we are interested in finding its general solution. Okay, so we are going to use the method of Lagrange. Okay, there are other methods as well, Chapit's method. Okay, we are not going through right now. Maybe we may consider it later, maybe during the tutorial, we will see that. Okay, so you have this equation xp plus yq equals to z. So right hand side is, so this is a linear equation, I think so, right? This is a linear PD. So of course, if a linear PD, it is automatically quasi-linear. But quasi-linear PD may or may not be linear. Okay, right. So now, if you compare with this capital PP plus capital Q small q equals to R, what you will observe is P equals to X, capital Q equals to Y, and capital R equals to Z. Now, we are going to use the method of Lagrange. Okay, so we are going to find two families uxyz equals to A and vxyz equals to B for, so Lagrange equation. So these are called Lagrange's equation, okay? The Lagrange's equation for given PD, okay, problem or PD I'm writing right now, is dx by P is equals to dy by Q is equals to dz by R. Now, just now we have observed what are P, Q and R. So dx by X is equals to dy by Y is equals to dz by Z. So we have taken a very simple part. Now you take any two, okay, you are trying to obtain the solution, two family of solutions. You may obtain three. Okay, I'm going to work on that. So if I take first two pairs, okay, so I'm going to choose first two pairs, what it will give you? Dx by X is equals to dy by Y. You can use the variable separable method. Okay, so what it will give you the solution? What is the solution of this? Integrate both sides. Okay, variable separable method. So ln x is equals to ln y plus additional arbitrary constant, that is ln of c. So this will give you x by y is equals to c, or a, I suspect a. Now similarly, if I choose dx by y, sorry, not dx by y. So I'm going to choose the last two pairs, dy by y equals to dz by z. This will give you, again in the similar fashion, variable separable method, you have straightforward, integrate both sides, but and everything, as I think it will give you y by z equals to d. So you have two families of solutions. Okay. Now, but you may also say we can take this pair dx by x equals to dz by z. Of course, you can take. This will give you x by z equals to c in the similar equation. Okay, so you have these three family of solution, but you require for the general solution you require only two family of solution. Okay, so let's say u of x comma y comma z equals to x by y, v of x comma y comma z is equals to y by z, and let's take w of x comma y comma z is equals to x by z. Maybe z by x also you can write, it's not a problem. So it's equals to a equals to b equals to c. So now you can choose any two families. So you have general solutions like f of u comma v equals to 0. This will also give you the general solution by that result. Another solution is z of v comma w equals to 0. Another third solution is h of u comma w equals to 0. So any two will play the role. You can cross verify, okay? You can cross verify that if you going to work with this or this or this, associated PD will be the same. Okay, that you can cross verify. Okay, so finally you have solution like f of x by y comma y by z is equals to 0. G of you have y by z, x by z is equals to 0. H of x by y comma x by z is equals to 0. Okay. Now you will also see somewhere, okay, in the other textbook, another way of writing the solution, general solution for the Lagrange. If you find the two parameter family u equals to a and b equals to b. Okay, another way is u equals to arbitrary function of b or v equals to some arbitrary function of u. This will also define the general solution. We can also verify that. Okay, right. Yeah, so we have the one of the general solution is this. Right. Now let's take little complicated one. Okay. So let us consider the following. This is a quasi-linear PD. This is not a linear one. Okay. Now if you compare with capital PP plus capital QQ is equals to R. If you compare, you have capital Q equals to Z time X plus Y. Capital Q equals to Z time X minus Y. And R equals to X square plus Y square. Now, Lagrange's equation is dx by p equals to dy by q equals to dz by r. So this will imply dx divided by z into x plus y is equals to dy divided by z into x minus y is equals to dz by x square plus y square. So now, is there any way to deal with this problem? Straightforward is any pair will work out. So first two, if you look at first two, so if you look at the first two, that is dx by z into x plus y is equals to dy divided by z into x minus y. If you look at this, so z will get cancelled. And what you have is dy by dx equals to x minus y by x plus y. So this is a first order differential equation, ordinary differential equation, whose numerator and denominator both are homogeneous functions of same degree, that is degree 1. If you recall, you can use the substitution y equals to vx to transform it into a variable separable form. and you can find out the final solution.
Sir, but if we just cross multiply, we are getting like
We are getting,
y dx plus x dy form.
yeah,
And then
if it
x
is
dx.
there, that okay, so that I have tried. Okay, so if you cross multiply that also, if that works, that will be a nice thing. Okay, so we don't have to do more hard work. So x minus y dx, let's try that. X minus y dx is equals to x plus y dy. So what you will have is x dx minus y dx minus x dy minus y dy equals to 0. Now this is equals to x dx minus y dy, and this is minus y dx plus x dy. Yeah, we can do that. Now this is equals to, and this is equals to, I'm going to write is that d of x square by 2 plus, not plus, minus y square by 2 minus x into y equals to 0. Do you agree with this?
Yes, sir.
Right? So this will give you one family. So this implies if you integrate now both sides, what you will get is x square by 2 minus y square by 2 minus x into y equals to 8. So one of the family is now in your hand. Right? Now what? So one family is obtained. Now you have to obtain at least one more family. Okay. So now if you what we can have is, because since you have here x square plus y square, because see these problems can be handled if you do a lot of practice. Okay, which way you have to go. Now what I can observe is if you have let me write it further because here, so let's see. So what is the equation is dx by z into x plus y is equals to dy divided by z into x minus y is equals to dz by x square plus y square. Now can we because see there are various ways to try. Okay, one way is I'm going to try with it that let's take so this is further equals to, I'm writing x dx plus y dy divide by. So if you multiply, okay, if you multiply, what you will get? Z time x dx plus y dy. If I have multiplied this, so what you will get is x square plus xy plus xy minus y square. So this will not help you. Suppose you have minus here. So you have this is minus and this is plus, right? Correct? So this x dx I multiplied by x, okay, numerator and denominator. Here multiply by y, numerator denominator, and then subtract. Okay, so x dx minus, so this is equals to the following ratio. Okay, these ratios are equals to the following ratio. So x dx minus y dy divided by z into x square plus xy minus xy plus y square. Xy will get cancelled. So what you will have is x dx minus y dy divided by z into x square plus y square. Now I will choose these two pairs. Okay, because x square plus y square will get cancelled and you will have the simple form now. So if I choose now, so therefore dz by x square plus y square equals to x dx minus y dy divided by z into x square plus y square. Now this will get cancelled. So what you will have is x dx minus y dy minus z dz equals to 0. Now integration is very simple. Integrate both sides. So you have x square by 2 minus y square by 2 minus z square by 2 equals to sum b. Now you two can also be combined. So you have x square minus y square minus z square equals to 2b. So b is a generic constant. So I mean write it b. So another family is this. Okay. So finally what will be? So u equals to one solution is x square by 2. So you can also move this 2. So x square minus y square minus 2xy. X square minus y square minus 2xy is equals to a. And v equals to x square minus y square minus z square equals to b. Two family. So you have f of u comma v equals to 0 will be the general solution. So there may be a chance that you may also find out different family, okay, for forming the solution. Okay, not that these two are not scalar multiple of each other, that you have to keep in mind. Okay, u and v should not be related, they should be independent. Okay, and that can be easily find out when you have more than two variables. Okay, so one of the solution is so another here one more solution is given 2 type xy minus z square. Okay, so that is also somewhere is, yeah, that is also somewhere that may have some come from the some other pair. Okay, right. So one pair we have this another family 2xy minus z square is a w is equals to 2xy minus z square. That you can also try. Okay. Right. Now you have the following problem. So it will be a little more complicated now. Okay. So if you again compare with the this standard form of quasi-linear PD, okay. So what will we obtain is capital P equals to x into z minus 2y square, q is equals to y into z minus y square minus 2x cube, and r equals to z into z minus y square minus 2x cube. Now I am writing straightforward the Lagrange equation dx divided by x into z minus 2y square dy divided by y into z minus y square minus 2x cube equals to dz divided by z into z minus y square minus 2x cube. So I think one family is straightforward by looking at the last two pair. Okay, by last two pair, if you look at the denominator, this last factor will get cancelled, And dy by y equals to dz by z will give you the one family. That is very easy. So last two pairs is good. So from last two pair, is dy by y equals to dz by z. Other factor is get cancelled. So if you solve it out, this will give you ln of y equals to in the similar fashion. So you have this is y by z equals to some a. So you got this u is equals to y by z. Now for the other one pair, what you can do is yeah. So any other pair which you can work out. So straightforward, there is no pair. Okay, certainly. What else you can look at is you can't look at x dx plus y dy. I think so because it may complicate more. We want to get simplified one, okay, in the denominator. Yes, what we can do is we can get rid of this z somehow, okay, in the denominator by some I think so, by subtracting, but I don't know how much it helped us. Okay, let's work out the y dx minus x dy. So you have dx divided by x into z minus 2y square is equals to dy divided by you had y into, right? Yes, y into z minus y square minus z minus y square minus 2x cube is equals to dz divided by z into z minus z into z minus y square minus 2. Okay, so if you look at this equals to y dx minus x dy divided by, so you have xyz minus 2xy cube, that's the first one, minus you have, this is here, this side is xyz minus xy cube minus 2 y x to the power 4. God. Okay. So x into y into z will get cancelled. Whether we can further simplify it, y dx minus x dy divided by You have x into y cube minus 2xy cube. And this is minus minus plus. So what you have is 2yx to the power 4 minus xy cube. Okay. Now this is equals to y dx minus x dy divided by, now this is x into y into 2x cube minus y square. So this is what we have obtained. Can we use that? I don't think so. Okay. I don't think so. We can use this. Okay, because we don't see any simplified numerator or denominator in the other pair. Okay, so we have to definitely try with some other pair. Okay. Okay, so what you can do is you can do exercise this and try to get that pair. Okay, we will see in the next class. Okay, the same pair. Okay, if you are able to find out, you can post it on Google Classroom. Okay, or else we will see in the next class. Okay, this time is over. Okay, right. So if you have any other question, you can ask. Hmm.
Means if we directly try to cross multiply and then try means instead of this manipulation.
Yeah, you can. It's like any two pair you can do, and you can just cross multiply and see if you are able to get a simplified form, and if you are able to integrate, that is perfectly fine. Not that z is depending on x and y.
Oh, yes.
Ah. Okay.
Means that will create problem if it is in the
Yes.
dx or dy.
Yes.
Yes. Okay, sir.
Okay. Yeah. Thank you.
Thank you.